Welcome. In this more advanced exercise, we're going to use regression analysis to model a relationship between an outcome, which is a binary variable. So if what we're trying to predict is not a continuous variable, but rather a binary variable, such as in this case, let's say we've got two categories, 0 and 1, then we actually have what we call a classification model. And it's called classification because you're classifying a certain observation into certain sets of categories. So to make things more concrete, I'm just going to scroll below to show you the data that we're going to operate on and then come back to the diagram above. In this data set, which is the diabetes data set we've seen before, the main outcome is whether the patient is diabetic or not, which is 1 or 0. And we would like to make this prediction using a couple of predictors, such as those diagnostic variables we have about the patient. Now, if you take a look at this figure in here, when you've got an outcome which is binary, if you try to fit a linear function to predict this outcome, you're going to get a straight line. And there are a couple of problems with this straight line. One of the main problems with a straight line is that the straight line is not bounded. It can go from minus infinity to infinity, which basically means that when you're making prediction, you're not guaranteed to get 0 or 1. You're going to get anything. So, and what you're getting doesn't have a natural interpretation. For example, what does it mean if you predict the outcome to be 2.5? Right? What does it mean if the outcome is 0.5? What if the outcome is minus 100, which is possible because if you fit a line, that line will extend, and depending on the values of the predictors, you can get anything. So that interpretation doesn't have any natural interpretation given the two categories. The other option is to drop regression analysis completely and use other models to that a statistical model that yields categorical outcomes, such as decision trees, for example. That's something we will not take a look at here. This is something we will revisit in the second part of this course. However, it's still possible to use regression analysis with a simple trick. And this trick is a function that converts this unbounded line to a bounded, in this case, curve, which goes from 0 to 1. Now, I'm not going to talk about the theory here. There are a couple of functions that allow us to do this conversion. And one of the functions that is used to make that conversion is called the logistic function. So this logistic function will basically, given a line, give you this S-shaped curve. So what's unique about this S-shaped curve? Well, what's unique about this S-shaped curve is that it goes from 0 to 1. And this function also can give you anything in between 0 and 1. So on a first glance, you may say, well, but what does it mean, right? If we don't get 0 or 1, let's say we get 0.7, what does it mean? Well, what's nice about this function is that its interpretation is tied to the probability of the observation being in that category. So for example, if the value of this function is 0.7, it means the odds ratio of the observation being in category 1 is 0.7, and the odds ratio is the probability of being 1 divided over the probability of being 0. So that's a very useful function because it's kind of ties the interpretation of the outcome to probabilities, and we are guaranteed to get a prediction which is in between 0 or 1. All right, so the logistic function allows us to do logistic regression, which is actually a classification model. Although we've got the regression name here, you're basically trying to predict the probability of a certain observation falling into two categories with the predictors. All right, so let's take a look at this exercise here. Now, we've got a couple of predictors, such as pregnancies, glucose, blood pressure, skin thickness, insulin, so on and so forth. And our outcome is whether the patient is diabetic or not. And we want to predict the probability of being diabetic as a function of the other variables. So we're going to follow the same steps that we have applied before to run the linear regression analysis. First, I'm just going to double check that we have imported the packages, and we've done here. So we've imported statsmodel.api and give it the alias sm. And what I'm going to do now, I'm going just to create a model. But instead of creating an ordinary least square model for linear regression, right, that's the ordinary least square model, I'm going instead to create a logit model here. And that's for a logistic or logit regression analysis. What I'm going to do next is to use the from formula function. And then in this function, I'm going to try to predict outcome as a linear combination of the other variables. The only trick here is that I'm not predicting outcome, I'm predicting probability of outcome. And that's because I am using this logit function under the hood to convert the actual value from a linear value to a probabilistic value. Let's take a look at the columns in the data here. So I'm going to do data dot columns here, columns. So we need to make sure we have imported the data first. And if I do data dot columns, it's actually data 2 for some reason. So let's call this data instead data 2. So data dot columns. And what I'm going to do here, I'm going to relate this to pregnancies, glucose, blood pressure, skin thickness, insulin, BMI. I'm gonna put diabetes pedigree function, age, and obviously outcome is the outcome. I'm not gonna put outcome here. Let's not forget that we need to pass in the data we are using, so data equals data here. This whole thing is going to be our model, so I'm gonna store this into a variable called model. And if there are no errors, I should be able to run this code without issues. Now the next step is to fit the model to the data and store it in results. So I'm gonna call the function fit. So model.fit. Here I'm gonna get some kind of outputs here, and it says that the optimization terminated, so the model fit has been successfully completed. I'm going to print the model summary as I have done in the um, ordinary least square model. As we can see here, we've got the summary of the model, which is a bit cluttered here because of the space limitation. So I can either knock down the font size, or actually there is a function called summary2, which is a more condensed summary of the model. So let's kind of satisfy us now with summary2. And let's take a look at what we've got here. So we got some basic information about the model. Very importantly, it says the model has converged because this estimation requires some numerical computation and it's not guaranteed to converge. But this particular one converged, and we've got a pseudo R-square of 0.27% and other goodness of fit indices of the model here. And then we've got the coefficients here with their standard errors, the z-test for the coefficient, and also the p-values. So just quickly scoring through the p-values, we see that everything is significant except skin thickness and insulin. Also age as well. So it means that those predictors are not statistically related to the outcome in that case. But everything is related, such as pregnancies, for example, the coefficient is 0.1, glucose, the coefficient is 0.03, and blood pressure, the coefficient is minus 0.133. Now we started from the premise that when we have categories, in this case 0 to 1, we don't want our regression to make predictions that go all over the place, which is something we cannot see looking at the summary table here. The outcome, if we use this model to make prediction, is going to be in between 0 and 1. What's not very clear here is what's the relationship in between the coefficients to the outcome. When you say minus and positive, that will give you kind of the direction of the relationship. So basically speaking, a positive coefficient means this variable's increased value of this variable results into more probability of the outcome being 1. So pregnancy increases the likelihood of becoming diabetic in this case, or getting diabetes, or being diagnosed as diabetic in this case. Blood pressure in this case, which is interesting, decreases the likelihood in this particular data set, which is kind of goes against what we've probably expecting. But let's take a look at another negative variable, which actually is not statistically significant to interpret, which is taking insulin obviously reduces the likelihood the patient diagnosed as diabetic. But what does it mean for this value to be minus 0.012 or minus 8 or 0.03? The coefficient here is the log value of the odds ratio. So the odds ratio of a probability is the value of this probability divided over 1 minus the probability. So let's say you've got a biased coin, which comes head with a probability. Let's do this. Let's do head probability 0.8 and tail with a probability 0.2. Okay. So in this case, the odds ratio of head is going to be 0.8 divided over 0.2, and that's going to be 4. It means that heads are 4 times more likely to occur compared to tail. What we have here in coefficient is basically the log value of the odds ratio. So to be able to recover the odds ratio, we need to exponentiate those coefficients. So there are a couple of ways of doing this. I'm going to use NumPy, which is another package in Python that contains a couple of numerical functions. And I'm going to call on the function exp for exponentiation, and then I'm going to pass the model parameters, which is result.param here. Okay. So that's basically is going to give us the odds ratio of these variables. So when it comes, for example, to pregnancies, the odds ratio is 1.1, which basically means that being the odds ratio of becoming diabetic is 1.1. Okay, so it's not exactly 50-50. It's almost 0.55, probably the probability of becoming diabetes. Or you can go back to that formula here, right? For example, let's take a look at a coefficient which is really high in terms of odds ratio, which is diabetes pedigree function. 245, it means that it's twice and a half more likely to be diabetic if you've got this variable with each unit increase in this variable, which is diabetes pedigree function. If you take a look at age, each increase in age results in a slight increase in the odds ratio, right? So with age, you are more likely to become diabetic, but it's not that bigger change, right? You can run the number here. You can say, for example, p over 1 minus p equals 1.01, right? And then you can solve for p. If you solve for p, you're going to get the probability of being diabetics with each extra year increase in age. So I leave you that exercise here to kind of to finish. So once again, the logistic regression allows us to make a prediction for an outcome which is binary. And what's useful about this prediction is that it can be interpreted in the language of probabilities.